Hey, hi everyone, and welcome again to another video. So for this video, we'll discuss the simple and joint probabilities, mutually exclusive events, general addition rule, and the conditional probability. So let's begin with a simple probability. So actually, I've discussed this, but remembering again what are the basic categories of probability, we have the simple probability and the joint probability. So, a simple probability usually has only a single event or refers to a single event. Meanwhile, joint probability will be the occurrence of two events at once, no, simultaneously. So, an example of joint probability will be tossing two fair coins, or if a card is both an ace and a black card. No, so that's an example. So, mutually exclusive events, on the other hand, will be an event that occurs um uh non-simultaneously. So one example for this is when you pick a card, no, a single card from a deck of cards, you can pick or there's a possibility that you will pick one king card or one queen card. So yung the events of this two events happening will be mutually exclusive, since you cannot pick a queen card that is also a king card. Okay, so again, it is mutually exclusive because you cannot pick a king card, no, so a single card that is also a queen card. So it could only either be a king card or not a king card, no, which is one of the not a king card will be a queen card. So they are mutually exclusive. So let's have an example or further example of this. So consider an experiment where two fair die are rolled. Three events are defined as follows. So the sum of the two numbers on the die is 7, and then the sum of two dice is 10. And then each of the two die shows the same number. So for the event A, so what are the cases here for event A? So for event A, we have what are the numbers that could be a part of this? So we can add 1 and 6, right? So the die will get 1 and the other die will get 6, and then it could be an alternative, no, or it could be vice versa. So this could be 6 and 1. Okay, so sometimes the die will roll 1 first and then 6, no, and then it could be 6 first and then 1, and then it could be 2 and 5, 5 and 2, no, and it could be also 3 and 4 or 4 and 3. Yeah, so this will be the scenario for event A. For event B, the sum should be 10. So the first one is the lowest possible first pair is 4 and 6, and alternatively 6 and 4, or even 5 and 5. So we cannot swap 5 and 5 now, so since they are the same for the two die. Okay, so that is for event B, and then for event C, if the two die shows two numbers equal, no, so we have 1 1, and then we have 2 2, and we have 3 3, and then 4 4, 5 5, and 6 6. Yeah. So the question here is, given this three events, are they mutually exclusive? No, so we can inspect if A and B are mutually exclusive. So if they do not have an intersection, then they are not mutually exclusive, or they are mutually exclusive. So as we can see here, there is no intersection, or there are no similar events here. So therefore, we can say that A and B A and B are mutually exclusive. So there is no similarity. Okay. For event B and C, no, is this mutually exclusive? So there is an intersection, ano? Then therefore B and C are not mutually exclusive. Mutually exclusive. And then for, let's say, A and C, no? So comparing these two sets or two sample space, do we have a similar set here? So we do not have a similarity between these two events. Then therefore A and C are mutually exclusive. Mutually exclusive. So what can we say about these three sets? So if we combine these three sets or if we analyze these three sets, what can we say about them? So they are not mutually exclusive, since again we have a similarity with B and C, and that's it. No, there is a similarity with B and C. So therefore, we can also say that A, B, and C are not mutually exclusive. Okay. So let's see the representation of this using a Venn diagram. So using a Venn diagram, if they don't have a similarity, then they are mutually exclusive. So exclusive means they are excluded from each other. No? If they are non-mutually exclusive, then they will have an intersection in between or a similarity between their sample space. So for collectively exhaustive events, so there are events that can be categorized as collectively exhaustive if those events can cover the entire sample space. So meaning if let's say we have 4 events here, so let's say an event could be picking an ace card, picking a black card, picking a diamond card, a heart card. We can say that A, B, C, and D are collectively exhaustive, no? So why is that? So if you pick a card, it could be an ace, it could be a black card, it could be a diamond, or it could be a hearts. So you can imagine that at least one of these events will occur if they are collectively exhaustive. So you can either pick a black card, ano? So meaning the sample space left there will be the red cards, and we know here that the diamonds and the hearts are the red cards. So these are the black cards. These are the red cards, diba? So how many black cards do we have? So we have 26, right? Which is also 26 for the red card. So meaning this is the total of the sample space, excluding even the aces, no? Then they are collectively exhaustive. So including the aces, this will still be collectively exhaustive kasi from this pa lang, no? Meaning aces doesn't really matter here. Okay? But as you can see, events B, C, and D are collectively exhaustive and mutually exclusive. So meaning it could be a black card, it could be a heart card, or it could be a diamond card, and there won't be an intersection. But for aces, no, if you include aces here, there is an intersection between the diamonds and the hearts and the black cards. No, so the ace can be a black card, it could be a diamond, or it could be a heart. So that is the collectively exhaustive events. So we can add a principle to this, wherein the probability of a joint event from happening, meaning it has a characteristic of both A and B events, as the probability is equal to the ratio of the outcomes that satisfies both, no? So meaning both, okay, or intersection, and then the total number of elementary outcomes. So meaning the sample space. And then for computing the simple or marginal probability, we have this, assuming that this B here, this B event here, are mutually exclusive and collectively exhaustive events. So let's just have an example now. It doesn't really make sense here. What does it mean, no? So let's say we want to find the probability of drawing a card that is both red card and an ace card. So how many cards in the deck are both red and ace? No, so we have two, right? Versus the total number of cards. So we have a probability of 2 over 52, or we can simplify this further as 1 over 26. But if we remember the contingency table, we can visualize this probability that we have this intersection between the red and the ace card, no? So that will be the probability for a joint probability that is non-mutually exclusive. Okay, so another example here is using this table provided, what is the probability that the customer is male and is under 20? Okay, so how do we do this? No, so the best way to do this is just to examine this. This is a contingency table, no? So we have the age group for this column here, and then we have the gender, no, for this row here. So we want to determine the probability that it is male and under 20. So therefore, we want to find the intersection with this, sorry, not that, no, but with this and this. So therefore, we have a total event that is 42, and the sample space will be everyone else here. So we have the total 200. So we have over 200 as our probability. Therefore, this will be the probability 42 over 200. Now, if we want to now find out what is the probability that the customer is female. So the customer is female only, no? So this will be your probability, or in other words, the total of this is equal to this. So therefore, this will be 104 over, 104 over 200. Okay, so 200 is the total of our event or the sample space. Now, we can actually rewrite this in some way that is consistent with the law mentioned earlier, wherein the probability of an event occurring for B exclusive events that is collectively exhaustive is this. Ayan. So, as we can see, we can also write this down as 40 over 200, which is this, and then 36 over 200, which is this, and then 28 over 200. Yeah, right? So that we have a probability of 0.52, which in other words is still the same as this. Okay? So, moving on, we have the general addition rule. So, if you have two events that can occur that are A and B, so events A and B can occur, the probability of that happening, A or B happening, is the sum of the probability of A and B happening minus the probability of A and B occurring. So, we will make sense of this later. Why do we have a term here? So what is this? Again, this is the intersection. Okay. So if we can say that A and B are mutually exclusive, meaning they are independent of each other, then the probability of A and B happening will be 0. Then we can simplify this rule as just the sum of the probability of A and B happening or occurring. So let's say, for example, we want to determine the probability of picking a red card or an ace card. So the probability of this occurring will be the sum of their probabilities, no? So we have, how many red cards do we have? We have 26. For ace, we have 4 ace. And then minus their intersection, meaning when do they intersect with each other? What are their similarities? So there are two cards that are red and ace, which are the ace of hearts and ace of diamonds. Okay, so we have 2 here. So therefore, this will be calculated as this. So we have 28 over 2. And if you visualize this using a contingency table, the sum of the red cards is this. So we have 26, so 2 plus 24. And then for the ace card, if you have 2 plus 2, which is 4 in total. So 2 red cards, 2 black ace cards. And then the intersection, as you can see here, is the 2 cards. So for counting how many cards is in the probability or in this sample space, no? Or in this event na lang, no? So for this event, then you should not count the 2 here. So we have to subtract the extra 2 that is the intersection between the 2. Okay, so you can see that this will be 26 plus 2 only. So we have to subtract the 2 from this 4 so that we have an actual calculation of the probability. Okay, so another example here, what is the probability of counting or the probability of drawing a black or a face card? So it could be either a black or a face card. So we have 26 black cards and we have 12 face cards, and then the intersection between the two. So how many face cards do we have? So we have Jack, Queen, and King. So we have 3 cards. So how many black cards of Jack, King, and Queen? So we have 2 pairs. No, it could be either a spade or it could be a club. No, so 2 times 3, we have 6. So therefore, we have to subtract that intersection between the two so that the probability is 32 over 52. Okay. So we can also utilize the general addition rule for real world scenarios such as this, no? So let's say we have a simplified circuit diagram in which 2 components A and B are connected in parallel. The circuit functions if either or both components are operational. From past data, it is known that the probability that component A is operating is 0.99, the probability that component B is operating is 0.98, and the probability that both components A and B are operating is 0.9702. Find the probability that the circuit is functioning. So basically, what is a circuit? So a circuit is just basically a network, no? We can imagine this as pipes, no? There is a pipe or there's a water flowing into your circuit, so there is a directionality. So the probability of A occurring will be 0.99, so meaning 1% of the time it might not be working, and then for B it is 0.98. Okay, so together, to know that they are working together, okay, so this will be 0.9702. So the probability of them working together is 0.9702, which is actually just 0.99 times 0.98. No, it is not explained here, but this is just the multiplication of the two probabilities. And what should we add here? So the question here is, what is the probability that the circuit is functioning? So how does a circuit work? You know? So a circuit works when there is a current flowing. So there should be at least one. If you say that the probability, no, is functioning, there should be at least one. At least one functioning. So ibig sabihin, no, what we're trying to find out is what is the probability of A or B occurring. So therefore, the probability of A or B occurring will be this general addition rule. So we have the given probabilities, 0.99, 0.98, and the intersection between the two, which is 0.9702. So therefore, the probability of this occurring will be 0.9998. Okay, or 99.98%. Okay, so for the last portion of the video, let's discuss the conditional probability. So, the conditional probability is just another way of exemplifying joint probabilities, no? Or a similar way of treating joint probabilities. So the probability of event A, given that if B has occurred, okay, again, the probability of event A given that B has occurred is equal to the probability of A and B occurring over the probability of B. Same as when we exchange this, no? Vice versa, the scenario is, what is the probability of B occurring given that A has happened is equal to the probability of both A and B happening over the probability of A happening or occurring. So a conditional probability, we can visualize this as what do you call this, a process, no? So let's say you have event A and event B. Okay, you have event A and event B. So the probability of B occurring is dependent on the probability of A occurring, right? So if this is a process line in the industry, for B to occur, A should occur first. So there is directionality. So to find this probability of B occurring, so the probability of B occurring, given that A has occurred, which is this event, then this is equal to the probability of A and B happening over the probability of, sorry, not this, but the probability of A occurring. So this should be remembered, guys, no? The given A is also the denominator for the formula. Now, let's have an example here. So what is the chance that you would get a 6 given that you have gotten an even number? So what can we say here? So the sample space is just 1 to 6, right? And the probability of that we're trying to find is the probability of A given that B as equal, no? So we can imagine that A event is that you will get a 6, right? And then the event B will be even numbers, no? So given that it is even numbers, is we have 2, 4, and 6. So the probability of A occurring, which is 6, given that B has occurred, will be equal to the probability of A and B occurring over the probability of B occurring. So basically, what is the probability of A and B occurring? So basically, if you want to find the probability of A and B, that is just the intersection. So the intersection of these two is 1, no? So we have 1 out of all the sample space, so we have over 6, right? And then the probability of B occurring, okay, that is equal to how many of is this compared to the sample space. So the sample space is always 6 since we just rolled a die or a dice. So this will be 3 over 6. So therefore the probability of this happening is 1 over 6 all over 3 over 6. Ayan. So we can cancel out the 6 here. So we have 1/3. Okay? So the probability or the chance of this happening is 1/3. So of the cars on a used lot, 70% have air conditioning and 40% have a CD player. 30% of the cars have both. What is the probability that the car has a CD player given that it has an AC? So of this things, we want to find the probability that a car has a CD player given that it has an AC. So we can already say that the event A, well, we can assume that the event A is the CD player, and the event B is it has an AC. So we want to find out the probability of A given that B has happened. Ano? So we want to find the probability of A and B occurring, right? So A and B occurring over the probability of B occurring. So how do we now understand, or how do we utilize these numerical values? So 70% have air conditioning equipment. So that is a total, right? So we can create a contingency table since it is not explicitly said what are the intersection of this and also the probability of B. Is it? no? So we want to create a contingency table to just exemplify this problem. So we have here, it could either be a CD or not CD. It could have an or sorry, no CD pala, no? So we have AC or no AC. So what is the total, no, that is given? So we have 70% have A of the domain. So it could be either C with CD or no CD. So we have 70% of them that has some AC. So it could be a sum of any two percentage, okay? And then 40% have CD players. So this is a total for the CD players. So we have 40% here. And then 20% have of the partial vote. So this will be they have both CD and an AC, you know, so there is an intersection between these two. So this will be your contingency table. So we can see that this will be just 50%, right, as your additional information, because the sum of 20 and 50 is 70. And then for this one we have 20, okay, because the sum of this should be 20. And then for the total, so this should be 60%, right? So therefore this should be 10%, because this will be 100%. Now if we add this, and then for this one this will be 30%. Okay, so we're trying to find for the probability that A and B has occurred over the probability that it is C. So we can imagine that it has an AC, so the probability of B occurring is 70%, so 0.7, and the probability that it has a CD player, so this will be what? No, it is actually just 20%. No, so the probability of A and B, the probability of A and B is 20%. So this will be 20%, or 0.20. So therefore this will be equal to the probability of A occurring given B has occurred is 0.2 over 0.7. That is about 0.2857. That's it. Okay, and then another example here. So using the table, what is the probability that the customer is 40 years old and above, given that she is female? So again, we have to find the probability of A occurring given that B has occurred, which is the ratio of P of A and B over P of B. Okay, so the event A here is, it is 40 years old, so 40 years old and above, and then B here is, it is female, or the person is female. So B here will be what? No? We have the probability that it is female. So the probability of it of the person being female is 104, which is the total here. So the P of B is 104, and the probability that it is 40 years old and it is female, so both, that is it is female and it is 40 and over, is 28. So therefore this will be 28, no? Okay, so this should be over 200 and then over 200, but anyways this will cancel out, no? So this will be the ratio of, again, P of AB and P of B. So we have 104 over 200, sorry, 28 pala, no? 28 over 200 and then 104 over 200. So this should be equal to we have 0.2692. Ayan. Alright, so with conditional probabilities, there is a dependence between event A and the event B. So usually in this scenario, A is dependent with the event B. So the B scenario should occur first before the event A. So if they are independent of each other, meaning the probability of A can occur outside of the occurrence of B, then they are called independent. And the probability of A occurring given that B is occur, that B has occurred is just the probability of A occurring. So that's it. I think that will be the last for that example. Now we have further properties. Now we can simplify the probability. No? So if you could remember the formula, we have the probability of A given that B has occurred is P of A and P over P of B. So if we do the cross multiplication, you can see that the probability of A and B occurring is the probability of B times the probability of A given that B has occurred. So therefore, we can write this equation into this form. So we can find the intersection of your you can find the intersection also. It could be it should be A or B. Actually, it could be alternate, no? So this is the same as this. Okay, it can be alternative or it could be alternate, but this one cannot be alternate, no? It is not the same with this term here. Okay, so if A and B are independent, then the probability of A and B occurring will be the probability of A and probability of B multiplied. So this is the multiplication rule. Kindly remember this. So for this example, we have a scenario wherein we want to determine the probability that he will open the door, you know. So let's imagine a man with 6 keys. So one of which will open the door. So you have 6 keys and only one will open the door. If he tries the keys at random, so randomly, and then discarding the first key that did not work, what is the probability that he will open the door on his second try? Ano? So let event A is the event that will occur on the first try, and the B event will be the second try. So for the event A, this is when he opens the door in the first try. So it will be only in the second try if it is not the what do you call this? If it is not the key that he chose, no, it is not the right key. So therefore, the probability that we are trying to find is the probability that it will not open on the first try and it will open on the second try. Do you get that? So it will not be not open on the first try, and then B will open on the second try. So the intersection of A and B. So therefore, we're trying to find the probability of A not occurring, okay, and the probability of B occurring given that A has occurred, or the not of A has not has occurred. So what is the probability of A occurring? So for this one, it will happen on the first try. So meaning you have 6 keys. So we have only one correct key. So we have 1 over 6. Therefore, the probability of A not occurring will be the complement of this. So we have 1 minus 1 over 6. So this will be 5 over 6. Or sorry, A prime. 5 over 6. Now, for him to open, or her to open that key, given that A has occurred, will be what? So given that he did not open it on the first try, meaning he is left with 5 keys only, no? So for this one, he has 5 keys left, and one of those are the right key. Diba? So therefore, the probability of this occurring will be 1 over 5. So this will be equal to 5 over 6, which is the probability of A not occurring, and then the probability of B occurring given that A does not occur is 1 over 6. So isn't that interesting that when you open the door on the second try, it will still be the same probability as when you first tried it, no? So on the first try, you will open it 1/6 of the time, but for the second try, it will still be 1 over 6, given that you did not open the door on the first try. Isn't that interesting? So it is the same thing, right? Okay. So that will be all for this video. So I will see you guys in class, and good luck.